Good morning, afternoon, and evening. Welcome to the Week 3 for S2S monthly webinar. Today's session features two distinguished speakers, Dr. Song from NOAA GFDL Princeton University and Dr. Fu from NOAA EMC. For further details, Dr. Song, please close down another speaker, otherwise it will be echoed. Okay. For further details, kindly refer to the Week 3 for S2S website provided in the chat box. Additionally, we encourage active participation through the discussion document available in the chat box during and even following the webinar. Both speakers will contribute to addressing any questions or comments you may have. So looking ahead, our next webinar is scheduled for July 1st at 2 p.m. EDT. Okay, let's introduce our first speaker, Dr. Song. You can start.
Hello, can you hear me?
Yeah, it's now clear. Go ahead.
Okay, great. Sorry for the technical issue. Hi, everyone. Thanks for the opportunity to present our recent work. My name is Qianqian Song. I'm a postdoc at Princeton University, working with Dr. Paul Ginoux at GFDL. Today, I'm going to present our recent work on modeling impacts of dust mineralogy on fast climate response. So before I start, I would like to thank all our collaborators and funding support from SIMS program and the EMIT project. Here is the outline. I will start with the motivation of resolving dust mineralogy in the climate models. And then the second part, I will discuss the dust optical properties before and after resolving mineralogy and their comparison with observations. So this part of a study will lead to a recommendation to reduce dust absorption in our climate models. And the third part, I will discuss the impacts of reducing dust absorption on fast climate response. We know that the aerosols can impact climate through different ways. In this study, we focused on the impacts on climate by direct interaction between dust and radiation. And this is usually called dust direct radiative effects, and we simply call it dust DRE. And many previous studies have suggested that dust DRE is largely uncertain. As we can see from this figure on the left, it's from Lee et al. 2021 study. This figure shows several previous studies about dust shortwave, long wave, and net DRE calculations and their uncertainty. So we can see how large the uncertainty is. In panel C and panel D, the uncertainty is only from mineral composition uncertainty. So we can know the mineral uncertainty composition, mineral composition uncertainty is very important for dust DRE uncertainty. In the figure on the right, is from my previous study, 2021 study. In this study, we calculate dust DRE and the uncertainty contributed from each individual uncertainty source. For example, the refractive index, size, and shape uncertainty. So from this study, we can see dust DRE uncertainty is mainly attributed to dust refractive index uncertainty, and dust refractive index is controlled by dust mineral composition. So overall, we know dust can affect Earth radiation through dust DRE, and the DRE is largely uncertain, and this uncertainty is mainly attributed to dust mineral composition uncertainty. So it's important for us to understand the dust mineralogy. Also, we know soil mineral composition varies across dust source regions. As we can see from this figure on the left, it shows the dust emission from several major dust source regions. And the figure on the right is from the Biagio 2017 study. They measure the soil mineral composition from those dust source regions. We can see there is a large spatial variation in the soil mineral composition. So the dust aerosols emitted from those source regions will also have large spatial variation. However, most climate models, including GFDL, still use fixed dust mineralogy, which is the globally uniform dust mineralogy. So it is important to resolve dust mineralogy in models to investigate dust radiation interaction. So in this study, we implement 8 minerals and activate their interaction with radiation in the GFDL AM4 model. In other words, dust is speciated into 8 minerals in this study. And here I list the 8 minerals. They are iron oxides, which is represented by hematite in this study, and the 3 clay minerals, the feldspar, gypsum, calcite, and quartz. Among all those minerals, hematite content controls dust absorption in visible spectrum. So it's important for us to understand the hematite content in dust. And I will discuss this hematite content a lot in the following slides. So then we conduct 3 experiments using GFDL AM4 model. The first experiment is the HD27 experiment. It represents the homogeneous dust with 2.7% hematite content. So in this experiment, dust mineralogy is spatially and temporally uniform, and it represents the dust in the standard GFDL AM4 model. And in the second experiment, it's called HD09. So in this experiment, dust mineral composition is still a globally uniform value. And we reduce the hematite content from 2.7% to the 0.9%. And the third experiment is called BM experiment. And this is the only experiment we resolve dust mineral. And in this experiment, dust is speciated into 8 minerals. The hematite is considered as internal mixture with clay minerals, and all other minerals are externally made. So we ran those 3 experiments for 19 years with historical run and with observed sea surface temperature and sea ice and CMIP6 forcing. Considering that hematite content is important for dust absorption in the visible, so here we show the global distribution of hematite surface mass fraction. The left figure shows the hematite content in the mineral resolved experiment, which is the BM experiment. We can see it's not a globally uniform value, but for the HD27 and HD09 experiments, their hematite content are globally uniform. So here we show the difference between HD27 and BM experiment and HD09 between HD09 and BM experiments. So this figure in the middle suggests that HD27 dust overestimate hematite content worldwide compared to the BM experiment. And for the HD09, it overestimates hematite content in some regions, but underestimates in others. So, its global mean hematite content agree well with the global mean value in BM experiment. And then we further look at dust optical properties. So first we compare the modeled dust AOD with AeroNet measured aerosol AOD. In this figure here, the 3 markers represent the 3 experiments, and different colors represent the different regions. So we can see all those 3 experiments agree with AeroNet measured AOD to the same extent. And then we look at the dust single scattering albedo. We simply call it dust SSA. Dust SSA is a measure of dust scattering properties. So the higher SSA value is, the more scattering the dust is. So here we show the global distribution of dust SSA from the 3 experiments. We can see among all those 3 experiments, HD27 dust is the most absorptive. As we can see, it has the lowest global mean dust SSA value, and this is consistent with the fact that HD27 experiment has the highest hematite content, as we discussed before. And reduced hematite content in dust from 2.7% to 0.9% in HD09 experiment, and also resolved dust mineralogy in BM experiment. They both reduce dust absorption to the same extent. If we compare the HD09 and BM experiment, we can see given the same dust absorption on a global scale, resolving mineralogy affects the regional distribution of dust absorption. For example, resolving dust mineralogy decrease dust absorption over Taklamakan region and Iceland region, but increase dust absorption over Southern Hemisphere, especially over Australia region. And furthermore, we compare the modeled dust SSA with AeroNet retrieved dust SSA. Here we calculate the average dust SSA for the 3 experiments, as we can see here, those values shown here, and also calculate the average SSA for AeroNet retrievals. Based on this comparison, we can see the HD27 dust is overly absorptive compared to the AeroNet retrieved SSA. So reduced dust absorption in the HD09 experiment and the BM experiment improve agreement with dust SSA observations. In addition, if we look at the dust spatial variation, so because of the time limit here, I won't go into the detail, but this figure also suggests that resolving dust mineralogy slightly enhance dust SSA regional variability. So overall, we know reduced dust absorption improve the agreements with AeroNet retrieved dust optical properties. And then with those different dust optical properties from the 3 experiments, we first look at the impacts of resolving mineralogy on radiation. So here, basically, we compare the mineral resolved experiment, BM experiment, with the 2 homogeneous dust experiments. This figure on the left shows the, so here we focus on the North Africa region and the JJA season. And we can see the, because like dust aerosol is the most dominant aerosol type in this region, so we can see the most significant impacts over this region. So here, the figure on the left is the results from HD27 experiment, and the figure on the right is the difference between the BM and the HD27 experiments. And those dotted regions indicate the statistically significant regions. So we can see negative values almost everywhere. That means resolving dust mineralogy significantly decrease the net relative flux at the TOA compared to HD 27 experiment. And then similarly, we compare the BM experiment with the HD09 experiment. We don't see significant difference over this region. And furthermore, we compare the modeled clear sky net flux at the TOA with serious observation, and we can see reducing dust absorption in HD09 experiment and in BM experiment improve agreements with serious observation, as indicated by this table here. So here comes to the intermediate conclusion. So based on this part of study, the results indicate that more realistic dust representation can be achieved by decreasing dust absorption from 2.7% to 0.9% hematite content. We can use one single homogeneous composition, which is the 0.9% hematite content, rather than resolving for mineralogy. For the second part of my presentation, I will focus on the effects of reducing dust absorption on fast climate response. So basically, I will compare those two experiments, the HD27 and HD09. First, we look at the clear sky net flux absorbed in the atmosphere. The figure on the left is the result from HD27 experiment, and the figure on the right is the difference between HD09 and HD27. We can see the low absorption dust reduce the radiation absorbed in the atmosphere, which makes sense. And also, we further look at their impacts on the temperature. So if you look at those two figures at the bottom, they show the vertical profile of temperature difference between those two experiments. Now we can see the lower absorption dust has a cooling effect in the atmosphere over both Sahara and the Sahel regions, which means it decreased the temperature in the atmosphere. But if we look at the surface, we can see over Sahara region, lower dust absorption decreased the land surface temperature, but over Sahel region, it increased the land surface temperature, which is also shown here, the map on the left. So those opposite impacts on the land surface temperature over Sahara and the Sahel region reduce the temperature contrast between those two regions and achieve a better agreement with CRU temperature observation. So overall, reduced dust absorption improve the agreement with CRU temperature observation. And then we look at the surface wind pattern. Here, this figure on the left is the surface wind pattern from HD27 experiment. We can see over Sahel region, the onshore wind dominant. And the figure on the right is the difference between the HD09 and HD27 experiments. We can see the wind difference has an opposite direction as the onshore winds, which means the onshore wind over Sahel region is suppressed. That is because the lower dust absorption caused a cooling effect in the atmosphere, which means caused less warming in the atmosphere and suppress ascend, therefore suppress the onshore wind over this region. And if we look at the precipitation, we can see a reduction in precipitation over Sahel region, and that could be due to two reasons. The first one is the suppression of ascend over this region, and the second one is the suppression of onshore wind, as we discussed before. It brings less moisture to this region, therefore reduce precipitation over Sahel region. Over the Guinea coast region, we can see an enhancement in precipitation. One possible reason for this is that the suppression of ascend over the Sahel region can suppress the subsidence over Guinea coastal region, therefore enhance the precipitation over here. And also, we compare the modeled precipitation with CRU precipitation observation over those three regions. We can see reducing dust absorption in HD09 experiment worsens the agreement in precipitation with CRU observations over Sahel region. And this could be due to the omission of surface energy balance over the ocean, because in this study, we ran the AMAP simulation by prescribing the sea surface temperature. So here I want to briefly talk about some limitations in this study. So in this study, we use AMAP simulation. So we prescribe sea surface temperature. We didn't include the slow climate response in this study. And also there are some uncertainties associated with dust mineralogy. For example, the global distribution of dust mineralogy is from Qianqian 1999 study, and that study is based on a limited number of observations and extensive extrapolation. And also there are some uncertainties associated with the optical properties used for each mineral and their mixing states. So in terms of the limitation of the dust mineralogy global distribution inventory, the observations from EMIT instrument, which was launched in 2022, will provide observational constraints on the global distribution of dust mineralogy. And this video here is provided by Dr. Paul Ginoux. It simulates the light absorption by different types of minerals. And it is a simulation by using NOVA JFDR AM4 model with the first version of EMIT soil map. Thank you. So yeah, this is all I have. Thank you for your attention.
Oh, thank you, Dr. Song. Yeah, because even with the technical difficulties, you delivered quite well with the precise time limit. Dr. Song, please, please close down. Another speaker. But anyway, so I have a quick question. Any airborne observations of dust are coordinated with the modeling efforts?
Sorry, any L1?
Airborne aircraft observation of the dust. The reason why I'm asking is NASA has an air quality program with the South Korea, and they're measuring the dust source in the West Sea of the South Korea. So I think like your outlook is kind of global. So any kind of airborne observation of dust are coordinated with your modeling experiments. If it is available, I'm just questioning.
So I think in our current study we didn't include any airborne measurement of dust, but we so we include some laboratory measurements, some in situ measurement, but we didn't include the airborne. Yeah, it could be.
What kind of in situ measurements are being used?
So we use
the Ocean 3 or?
So for this part, for the dust optical properties, here we compare with AeroNet retrievals. Actually, we have another comparison with laboratory measurement, and we got similar results, but I didn't show here.
Okay.
Yeah, the laboratory measurement from DiBiagio studies. Yeah.
Okay.
They collect samples from several major dust source regions, and they measure the dust mineral composition in the laboratory.
Sounds good. I think any description of the involved in situ measurement would be helpful to the audience. That's my thought. But thank you so much.
Oh yeah. Thank you for your question. Yeah.
Yeah. Okay, let's move to the next speaker, Dr. Fu. Yeah, Dr. Song, you can close your window and then I will make Dr. Fu to be a presenter, okay?